Okay, ninth graders, I am going to walk through some of the problems for mechanical advantage and efficiency. This is a worksheet that you're going to be working on, but I'm just going to go through the even problems and you're going to do the odd problems. So number 2, again, we're talking about mechanical advantage, and we've done a lab with this. You've taken some notes on it, and it's the ratio of how much force out there is compared to how much force in. And if you have a mechanical advantage greater than 1, that means you have to apply less force to move something than it actually weighs, or how much force it would take if you just did it by hand. If you have a mechanical advantage of less than 1, then you actually have to apply more force. And sometimes that's an advantage because then you just have to do it for less of a distance. So anyway, let's get started on number 2. So here I have a force of 75 newtons and it's applied to a nutcracker to crack open a walnut. If the mechanical advantage of the nutcracker is 3.5, what is the force of the nutcracker applied to the walnut? It says applies, it should say applied. All right, so what do we know here? A force of 75 newtons is applied to a nutcracker. So that's the force somebody is putting in on the machine. So that's the force input. So Fn is 75 newtons. All right, then it says that the mechanical advantage is 3.5. So in this case, we know MA is 3.5. What does that 3.5 mean? It means that any force I apply is going to get multiplied 3.5 times by the machine. So what are we looking for? The force the nutcracker applied. All right, so the nutcracker is applying the output force, and that's what we're looking for. So if I look up here at my equation, I have MA, I have my input force, and I want to find the output force. So F out equals MA times F in. And now I can just substitute my numbers in. 3.5 will go in right here, and 75 newtons will go right here. And then I multiply those two numbers together, and I go 3.5 times 75 equals 262.5. And that is in newtons because that's the unit that we had already. Again, mechanical advantage has no units. So I apply 75 newtons of force squeezing that nutcracker to make the walnut crack. The nutcracker itself applies 262.5 newtons. So it's multiplying my force, and that's one of the reasons why we use machines. Okay, number 4. All right, to open a soda bottle, a force of 55 newtons is applied to the bottle opener. If the bottle opener applies a force of 675 newtons to the cap, what is the mechanical advantage of the bottle opener? So in this case, the bottle opener is a lever, it's a machine, and someone is applying a force of 55 newtons to the bottle opener. So that's our force input. All right, so then the bottle opener applies a force of 675 newtons to the cap. So the opener applies, which means that that's the machine doing or applying the force. So that's the F out, 675 newtons. And so then the question is, what is the mechanical advantage? All right, so now we go back to our equation, and MA is what we want. F out we have, F in we have, so it's F out over F in equals MA. And now we plug numbers in. So F out is 675 newtons. F in is 55 newtons. And let's get the calculator out again. 675 divided by 55 equals 12.27. We'll just say 12.3 for our mechanical advantage. And again, there are no units. The newtons canceled each other out. All right, let's go to number 6. All right, number 6, when using a pulley with a mechanical advantage of 1.5, a worker applies 250 newtons to the pulley. The pulley is used to lift a heavy crate. How much force does the pulley apply to the crate? So here we've been given, again, a mechanical advantage. And it says the worker applies 250 newtons. So if a person's doing this, that's the force in. And so the question is, how much force does the pulley apply? And that's the force out. And again, here is our equation. We have MA and we have force in, and we want to find force out. And since MA and F in are next to each other, we multiply. So that's going to be force out equals MA times F in. This is like number 2, right? And what was force out? That was our unknown. MA is 1.5, F in is 250 newtons. So plug those numbers in. MA is 1.5 times 250. And I won't get the calculator out for this one. This is going to be 375 newtons. All right, moving on, we're going to go to some efficiency problems. And efficiency is a way to tell you how much work you are getting from a machine compared to the amount of work that you put in. You might have to apply less force, but you never apply or do less work. In fact, you always do more work than you would have done just by lifting up the object. But it might not have been possible for you to lift a heavy object. You had to use a machine to do it, but you have to move it through a much longer distance. So efficiency tells us how does our work out compared to our work in. And it's always expressed as a percentage. So whatever number we get for efficiency is going to be a decimal, and then we multiply that by 100 to express it as a percent. So question number 8, a stage crew member uses a pulley system to lift scenery for the school play. If he does 750 joules of work and the pulley system does 600 joules of work, what is the efficiency of the pulley system? So we have to identify what is output work and what is input work. Input work is, first of all, always going to be the bigger of the two numbers. If it's not, then you have an impossible machine. But the other way to think about that is, if a person is doing work to a machine or applying force to a machine, that person is doing work, that's the work input. So the work input in this case equals 750 joules. The work output, the work done by the machine, that's the pulley system, is 600 joules. And so the question is, what is the efficiency? All right, so we look at our equation right here. E equals work out over work in. And we have to multiply that by 100% because that's how we change that decimal number to a percentage. So we go work out 600 joules over 750 joules times 100%. All right, well, 600 divided by 75 is 4/5. That same thing is 0.8 times 100%, and that works out to be 80%. So that's our efficiency. 80% of the work I do goes into lifting that crate. 20% of it goes into overcoming the friction that's in the pulley system. So it's wasted, it turns into heat, but again, maybe I couldn't lift that crate without the pulley system. So just because I have to do more work doesn't mean it's not easier, doesn't feel easier. All right, number 10. A ramp is used to load furniture onto a moving truck. The person does 1,240 joules of work pushing the furniture up the ramp, and the ramp does 822 joules of work. Calculate the efficiency. So the person does 1,200 joules of work, so that's work in. The ramp, the machine, does 822 joules of work. That's the output work. All right, and so then it says calculate the efficiency. So this is the same as the other problem we did. Doesn't hurt to do one more example though. So work out divided by work in times 100%. And that is 822 joules divided by 1240 times 100%. Again, notice the units of joules are on top and the bottom, so they cancel out. And I get my calculator out for this one, and I go 822 divided by 1240. Whoops, I gotta turn it on first. 822 divided by 1240, and that equals 0.66 times 100 to change it to a percentage, and that's 66.3%. So not as efficient as the one up here, but again, if I'm trying to haul a piano, I can't lift a piano up into a truck. This just can't be done, but I can push it up a ramp. I might have to go a longer distance and overcome a little bit extra more friction, but the machine makes it possible for me to do it. Okay, so you have the odd problems on this assignment, and let me know if you have any questions.